the quiz. Okay, please bring calculator. Okay, it may not require, depending upon the quiz, it may not require, but please, if it is required, then please don't tell that I cannot compute the correct value because I do not have. Please bring calculator. TA each student, but remember that we should bring sheets. Okay, so what we are going to do is, we have discussed about the classical probability axioms as well as the counting methods of arriving at the probabilities, wherein we have a sample space where the sample points are equally likely to occur, equiprobable sample points. And we will dwell with some of the problems which are called classical counting problems, which have been there in the history. It has been discussed, and that is, it has motivated people to work on these kind of problems. So we will look at some of the classical problems. First thing is that we looked at certain counting problems. There is one thing called as the circular permutation. So which is also something that I just want to emphasize. That is, the problem is like this one. We have got three couples. That is wife, husband. They come and occupy dining facility in a hotel. It's inherently a circular dining table which has got 6 seats. Like this. Okay? So they come and randomly occupy whichever seat they just get. The idea is we want to find the probability that wives are seated next to their husband. Okay, they come and occupy randomly, but just we are curious about what is the probability that all wives, they will sit next to their husband, either in the left side or right side. So this is the whole thing. So we will look at what are the different ways in which seatings can be done. If it were a linear one, the first position can be occupied by someone there are 6 ways of placing the first person here. There are 5 ways of placing the next person. There are 6 factorial ways in which they can be seated. But this is the circular one. If the waiter comes and then randomly looks at this one, whether there is nothing like which is the first chair, second chair, and so on. It's just an arrangement like this. The only way we can find out is whether someone is, as you move in the clockwise direction or anti-clockwise direction, what is the order? That is the one probably you can look at. Other than that, okay, if someone from the first couple's wife sit here and then we make this arrangement or sit here, there are only, if you do a circular shifting like this one, 6 ways of shifting, all will look the same. Okay, so which means that in this case the actual number of ways in which different arrangements that can be done is actually, for circular one, it is only 6 factorial ways by 6, that is only 5 factorial distinct ways of arranging in a circular. With this knowledge, what we can do is so the total number of ways is 5 factorial. So let's look at a problem of what is the ways in which our favorable condition will occur. All couples are such that they are seated next to each other. First we will take a couple of the time, C1, C2, C3, without bothering about the order of wife and husband sitting in which way. Okay. First, let us assume that couples are placed in this way. So again, if you look at the ways, there are 3 ways. If it were linear, there are 3 ways in which you can place the first couple here. Then there will be 2 ways and so on. So there will be 3 factorial ways of arranging the couples. In a linear one, But again in a circular one there will be only 2 factorial ways of placing the couples because it is circular. What it means is we have got C1 here, C2, C3. If I keep it, this is one way. The other way is C3 and C2. If we ask both are one and the same, C2 is here, C3 here, or C2 here, C3 here. Both are adjacent to C1. But they can be distinguished if you look at it whether it is clockwise or anti-clockwise. That is why there is a distinction. That is why basically there are 2 ways of only doing it. Okay. So 2 ways of arranging the couples. Then within each couple there are 2 ways of seating the husband and wife. So basically we have got the favorable number of ways is 2 factorial into 2 factorial. This is the probability that this is again there are many such problems. I am not going to look at all those combinatorial problems like number of ways in which maths books, physics books, which I have discussed. There are many such things. You would have probably encountered many of such things, and you can also work it out. Now we will only concentrate on some of the problems which are really interesting. Okay, one is called as the prisoner's dilemma problem. See here what happens here is that there are 3 prisoners, okay, we'll call them as A, B, C. They are put in a jail and you have a guard who just blocks them and keeps monitor them. There is a jailer who is in charge, okay. He comes one day and then tells the 3 prisoners that tomorrow morning one of you are going to be hanged and the rest 2 are going to be released. Okay, he only tells that much, and then tells to the guard and whispers probably who is going to be hanged and so on. But he tells to the guard that please do not give them any hint about their fate or whether they are likely to be released or likely to be hanged. You should not reveal that. You can talk to them anything, but no one should get a hint about that. If anyone gets, you will be hanged or you will be fired, whatever it is. So the God is very alert and so on. So he goes away. Then the prisoner A, B, C, they are all just sad and then they are looking at prisoner A alone thinks, okay, he comes and then approaches the guard and then says, can you please tell me whether I am going to be hanged? He says, no, I can't tell you. Can you tell me whether I may be released? No, I can't tell you. Because that will give you information. I can't tell you anything about your faith, anything that gives a hint about your faith. Then he tells that, okay, I will ask you a different question. Look, only one is going to be hanged, 2 are going to be released. I may be hanged or I may be released. Definitely, there is yet another prisoner who is going to be released. Is it clear? Apart from here, whatever happens today, there will be one prisoner who is going to be released. Tell me one person who is going to be released. That much you tell me. Okay? That is not, no, it's not no information about me. I am just asking about information about someone else. Why don't you tell them? That is not going to harm you in. He initially thinks and then he is about to tell, then he has a tire. He tells, no, I can't tell you. Why? The reason is, before even telling you, what is the probability that A is going to be hanged? What is the probability? Without knowing any idea, they are equally likely to be hanged. This is 1 by 2. Probability A released 2 by 2. Okay, this is what it is. Next, suppose I tell that B is going to be released or C is going to be released. Then if C is going to be released, he goes away from the picture. You will know that either A or B are going to be hanged. Okay? Then probability that you will be hanged becomes 1 by 2. Probability that you will be released becomes 1 by 2. Okay? So A being hanged or A being released, given that some answer, okay, B or C being released. This new information is 1 by 2. So this is actually what? As compared to this one, this is going to be larger. Okay, I am giving you, the information gets changed. So I cannot tell you anything. Okay, this is what the God tells this one. Then A asked, okay, have you done the course Ee3110? Says no, I have not done it. If I have done, I would not be in this question. Then it does, why are you asking? Because if you have read conditional probability and all these things, you will find that by telling this, you are not giving any additional information. The a priori probability is the same as the posterior probability. The conditional probability of whether I am going to be hanged or released will not change. And he said that I can prove it. This is what he does. So let us work it out. Is this clear that before anything, probability of A being hanged is 1 by 3, A being released is 2 by 3. Now let us look at a case. What is the probability that, okay, before that, okay, B and, so probability that one person is going to be hanged is 1 by 3. Probability then, if you look at those who are going to be released, okay, then there are 3 distinct paths, okay. Is it okay? Is also 1 by 3 because B and C will be released if A is hanged. Similarly, probability that A and C okay. Then what we are actually interested is, okay, well, then this is what happens. So then when he asks this question to the prisoner, he has to give an answer. What answer he can give? That depends upon the different, say, 3 scenarios. Okay, let's look at this scenario. When B and C are going to be released, means A is the one who is going to be hanged. Okay, if A asks, tell me someone else other than me who is going to be released, it can be either B or C. There are 2 possible answers. He can pick randomly one of the answer and give. So he can either say B or C. Rationally, we will assume that probability of that being to be B or of or being to be C. So we will put this one, okay, B and C to be released, and God says B is equal to 1 by 2 into 1 by 3 is equal to 1 by 6. Similarly, probability that B and C are going to be released and God says C is 1 by 6. Now let's look at this case. If A and C are going to be released, what answer will it God? God cannot tell anything about A because A is asking, you should not reveal anything about A. If A and C are going to be released, B is going to be hanged. He cannot tell B is going to be released. That is wrong. So the only person other than me who is going to be released is C, and he has to only tell C. Okay? Then probably that A and C going to be released and God says C. God says B is 0 actually, that I am not even writing. Is equal to what? 1 by 3 into 1. That is equal to 1 by 3. And similarly, probability that A and B are going to be released and God says B. Again look at it, A and B are going to be released. The God cannot tell A, he cannot say C because he is going to be hanged. His cat has to tell only B. So he has no other choice. So that probability of that, given this telling B, that conditional probability is 1, this probability is 1 by 3. So that both things happening is 1 by 3 into 1, it is 1 by 3. Okay. What are we supposed to find? Probability that A is going to be given that this is what we are interested in finding. Okay, so that is equal to, this is probability A given B. So that is the probability of So what is this? A is going to be released and God says B. See here, where does that happen? Here. A and B are going to be released, but A is, my thing is A is going to be released and God says B. That is 1 by 3. Divided by probability that God says B. Under what scenarios he will say B? Okay? And here is one, he will say B. Here is another thing and he will say B. So it is the sum of these two probabilities. He may say B as a result of this scenario emerging or this scenario emerging. Okay? They are all mutually exclusive because you look at this one. Okay? These are mutually exclusive. Within that, telling either B or C is all these, so the properties are up. So it's divided by 1 by 3 plus 1 by 6. The same thing we can do it for the other one also. Again the same thing, God says C and then so say this one. A is going to be released and God says C is 1 by 3 divided by probably that God says C is the sum of these two things, which is 1 by 3 plus 1 by 6. Okay, what is this? How much is this? 2 by 3. Okay, and originally also it was 2 by 3 because see, because see, there are 3 people, only one is going to be hanged. Okay, A is going to be released with the probability 2 by 3. So, if you look at this one, no additional information is being given. So, God can tell this answer. There is nothing wrong in that. Now let us look at another problem. This is called as the Monty Hall problem. Again, there is a popular game show which was conducted in West, probably US, okay, and it was conducted by one person called Monty, and if I am right, the name of the program is Let's Make a Deal, okay, and I'm sure you would have seen this many in Desi version of these shows in Hindi or regional language and so on. So the problem is like this: there are 3 doors. Okay, we will initially there can be 3 doors. We will number it later for convenience. So there is a contestant, there is the Monty is conducting the door. Only behind one of these doors there is a huge prize. Okay, it may be an iPhone or it can be a Skoda or a color TV, whatever it is. And the other two has nothing, some consolation prize, you call it as hat or donkey or whatever it is, it has nothing. So, Monty initially gives an option to the contestant and we randomly one door. And if I open and if there is a prize, you will get the prize from Monty. So, he chooses one door. Okay? And then what he does is he doesn't open the door and then tell what it is, and then that is not the way. The game has to be interesting. So what Monty always does is, suppose he has picked this door, then see, this may have price or it may not have price. If it has price, two other things are empty. If this has price, there is at least one that is empty. This is how it is. Okay. So whatever he chooses, Monty opens a door which does not have a price. Suppose this is the door that is open, that does not have a price. Tell that, look, this door does not have a price. We have chosen this does not have a price. Now I will give you an option. You can either stick with your original option of whatever this door, or switch to another door. Okay. What do you want to do? This is the usual way he does. Sometimes he does that, I will give you $1,000, you can now walk away without any billing, or you can continue to play and so on. Let's not look at those things. Only this. Now the idea is that should the player switch the door, or should he stick to the original option? Or it doesn't matter what he does. Now a quick survey. I should have asked survey for this. Okay. Quick survey. What do you tell? How many times he should switch? Very few only. How many say that he has to stick? No, because if you have to give me an option, please. Okay? How many says that it doesn't matter whether this way or one of this way? No, okay, it doesn't add up to the number M. Okay? See, the thing is, the argument, the straightforward argument is like this. To begin with, what is the probability this door will have a price? Okay. Well, before that, we will try to put some name for this one, ABC instead of that. Monty chooses, the contestant chooses a door. It may be this or that. To make it convenient, whatever he chooses, I will name it as 1. For example, this is the one he chooses. I will call this as door number 1. See, this one does not, I could have called it as ABC also. I'm just calling it as 1. Whichever you have chosen, I'm calling it as 1. Then Monty is going to open a door other than what he has chosen. That is definite. And the one which doesn't have the price. Whatever Monty will open, he can only open this or this. That doesn't have a price. That I will call it as 2. And what is left is 3. Okay? So this is what it is. Now the question is whether you should stick to 1 or switch to 3 or stick to 1. That is, this is all what is happening. Okay? Incidentally, this numbering 1, 2, 3 is arbitrary. Don't think that the contestant can only choose 1. There is no restriction on that. What he chooses, we are numbering. Only for the purpose of uniformly following this scenario. Well, to begin with, all doors are equal probability of having the price. Probability that door number 1, I will put it as price. So the probability that there is a price behind door 1 or door 2 or door 3 is 1/3. That is known. Okay. So the question is, okay, so if he chooses 1 which is fixed and if he opens 2, what is the probability that the price in behind door number 1, given that he opens the door, I will call this as open So, given that Conti has opened door number 2, what is the property, conditional property? The price is behind it. Similarly, what is the conditional property? This price is behind the 3, given that open. These two are you want to find out, then your answer will be clear. If this is larger, you switch. If this is larger, you stick. If both are one and the same, then you do whatever you do. It's fine. So, what is the probability that door 2 is open? Okay, we will see. If that a particular door that is open, okay, which you are numbering as 2. It's not that I have told that door 2 is open, this probability is 1. Don't think of that. A particular door is open. Is the probability that the price is behind 1 and then therefore 2 is open, or price is behind 2 and therefore 2 is open, and so on. If the price is behind 1, okay, then you could choose either 2 or you could choose 3. Okay, then probably the door 2 is open is 1 by 2. You would have chosen 2 with the probability of, because 2 or 3 you can choose. You would have chosen 2 with the probability 1 by 2, and probability that the price is behind 1 is 1 by 3. Okay, and probability that he will open 2 given that the price is in 2 is 0. If price is in 2, you would never open that, plus 0. And probability that he would open 2 given that the price is in 3, given that he has opted for 1. Clear? That is, if he has opted for 1, the price is in 3, then what is the probability that you would have chosen 2? It is 1, because he has to only choose 2. So that is 1 into 1 by 3. Right? This is the probability that this door 2 is open. What is that? We are doing the condition of, there are 3 mutually exclusive events, A, B, C's. We are asking that an event X, okay, can be written as P of X given A, P of A, plus P of X given P into P of P, plus P of X given C. This is how we are writing. Okay, so that is equal to how much? 1 by 2. Am I right? So what are we trying to find? Probability that price of A given B is in a similar manner you will have for in a similar manner you will have. So let's look at this one. Price is in 1 and he has opened to 2. Okay? And what is that we have got? Which we have got prices in 1. Okay? And he has opened 2 is this. Because the prices is in 1. He has chosen 1. So 2 and 3, 2 or 3 can be opened. Okay? Equal probability. So it is actually 1 by 3 into 1 by 2 divided by this one, which is 1 by 2. So then this is actually how much? 1 by 2. Okay. And then what is the other one? Price is in 3. And given that he has opened is what? Price is behind 3. Given that he has opened 2. And also that he has chosen 1. And this is 1. Right? This is the only way he could do. Given that, so sorry, we have to put this. So 1 is being selected and price is in 3. So he has to only open 2, no other go. So this is 1. And probability that he opens 2 is 1 by 2. Price is in 3. That itself is 1 by 3. And he has opened 2. This is 1 by 3. Right? Because this is, you have to multiply that. This probability is 1 by 3. And this probability is 1. 1 by 3 into 1. Divided by probability that you have opened 2, which is 1 by 2. So that is 2 by 3. So what it tells you is, the conditional probability that the price is 3 is 2 by 3, whereas the price is 1 is 1 by 3, which means that the contestant should switch the group. That is more profitable than sticking to the original. The way of looking at this, no, 1 is eliminated, still there are only 2. The probability of both of them is 1 by 2 is wrong. Okay? You can think about it, may look little bit like a riddle, but there are difference between these two things. Okay, one is without any knowledge you are doing, one has been removed. Okay, because he cannot choose what, he cannot open what you have chosen, and he will not also reveal the price. Okay, that forces him to choose something which is unlikely to have the, which will not have the price, so the other one has got more chances. That is what it is. Now, then we will look at one more thing. Let's say you have
sir.
Yes.
Yes. Sir, I think it shouldn't matter, sir. You can intuitively tell that it is the same as the prisoner's dilemma question, sir.
No, I understand. There is a right amount of analog you can try to draw, but
the probability that given that A is going to be hanged or released, let's say irrespective of A, we know that one person is going to be released. Similarly here, irrespective of what
it looks, that's why I wanted to discuss. It looks like they are similar, but they are not. There is no similarity. You follow through this math.
Sir, just once.
Huh?
Irrespective of what door you pick, you always know that one door is going to not contain a price. Similarly here, irrespective of whether A is going to be hanged or released, you always know that one person is going to be released.
No. So that's what a common sense reasoning may not give you the correct answer. Okay? Here, it gives you an idea about the other door, because of the rule that he will not open what you have chosen, and he will not open the price. That tells you more about the new occurrences.
So same way here, the guard doesn't tell the prisoner whether he is going to die or
No, it's different actually. If you want, I can discuss you at length later, because that's why I told you it is little bit of riddle. You can keep. First of all, it is paradox. First of all, it was age-old paradox. That is why you can keep discussing. Okay, you go through the solution and then I can discuss with you. Birthday problem is like that. Let us say one of your friend has called you for a birthday party of her 1-year-old daughter. And on one day, for example, tomorrow she has called, and then the birthday party goes on, and one gentleman approaches and then tells, hello, happy birthday. Incidentally, this is also my birthday. That person. Then you tell, oh, what a coincidence, okay? The same day you have the birthday of that of the birthday. And then you ask, what is the big deal about this coincidence? No, it's a very interesting thing. We have, of course, there are only 30, 40 people are only here. The probability that the birthday of two random persons being the same is very small. Ask, how small? What will be your answer? Probability that two random persons having the same birth date, not the, I'm not looking at the year. So, okay, 23rd June or 5th August, something like that. But month and date is also important. Okay. So what is the probability that that's what I am asking? What will be your answer?
1 by 3.
Give me 1 by
365.
1 by 360. Any other answer?
Sir, what are the total number of people?
Huh?
Total number of people in the party.
No, I am not telling that one. Probably the two random people. Or I will tell you, there are certain number of people. Let's say you have got 40 people. For example, in this class, what is the probability that two of you will have the same birthday? 90 people are here. If you put like that, 90 divided by 360, how much is 1/4 or something? Is it like that? I can tell you it's much more than that. It's not 1 by 365. If you tell it's 2 by 365, it is because you are comparing two people. It's all not.
Sir, it's 90 by 3.
Huh? 90 by 365. It's not like that. You will see how it is. So, like the probability that, let's say there are 10 people in the hall. The probability that their birthday falls in a particular day is equal to of matching one person. We will take one person. Okay. We will try to compute probability that none of them have got the same birthday. Okay. None of them have got the same birthday. So this is what you are looking for. The probability that the birthday of falling, let us say the birthday of one person is known, or probability that the birthday of another person falling on the same thing is. Okay, we will see first of all what is the total number of days in which the birth dates can happen. Assuming there are 365 days in a year, forget about the leap year, and so each person can have a birthday from 1st January to 31st December. Anywhere in this one, they are all right random. So it is 1 over 365. The second person can have the birthday with 1 over 360. Okay, it's just sampling without with replacement. So into 1 by 365 and so on. There are k people. So it is 1 by 365 over k. And what are we looking at? Probably that no match. Nobody's birthday match. For that to happen, okay, the way it can be done is the first person can have a birthday in any particular one. It can be 1 over 365. The second person's birthday should not coincide with birthday, but it can be in any one of the other. Okay? No, we are not 1 over 360. We are looking at the base one, not the problem. The first person can have birthday of his choice, anything, whatever it is, 365 ways of doing that. For that not to coincident with the other, the second birthday should fall only within 364, the third in 363, and so on, and the last in 365 minus of k minus 1. These are the only number of ways in which we leave that no match. So this is not a problem. Number of ways of distinct birthdays. So probability of no match is this is what how to do. So that we will write it like this. So this is 1. This I will write it as 1 minus 1 by 360. This is 1 minus 2 by 360. Right? So we have to compute it. Actually, we can put certain values of k and then find what the probability of match is. What I am looking at is, I want to find a value of k or so. Right? There is a 50% chance that the birthday of two people will match. Okay? So only that we can tell. What is the 100% chance means it will go to billion. It will approach 1 when k tends to infinity only. That is meaningless. We would like to find a value of k so that there is a 50% chance that two people will have the same value. Okay, you can try to put it, we will try to get an approximate. First thing is, if you look at e power of x, okay, can be written as and so on for x very less than 1. You can do a first order approximation as e power of x is equal to 1 plus some level, which is very small when x is very big. Okay, so for we are first talk about k maybe of 10, 20, 30 and so on. There are very less than 1/10 of it. So assume that this is a rough thing that we are going to get. So in that case, what we are doing is first some error is there. So e power of this thing. Okay, this is what it is. We will try to use that one. So this probability of no match is right? Because these are multiplying, the exponents get added up. Common is 365 and I have taken minus here. It is 1 plus 2 plus 1 plus 2 plus up to k minus e power of minus r. It's k minus 1 summation, k minus 1 into k by 2 into 365. This is what you get. Okay. So we can actually do some calculation, but it will so happen that for k is 23, then what happens here is e power of minus, this is 23, this is 22 divided by 2 into 365. So basically you are getting, this is 23 into 11, okay, 253 is e power of minus 253 divided by 365. Okay, you can find out this is 0.7 or it is something like that. This itself will be order of 0.49. So the probability of no match is 0.49 or probability of a match is 0.5 at least. Okay, this is what happens. See, I could have done the other way. Probability of no match is easy to find. That otherwise, what you have to do is, what is the probability that two people have the same birthday? That three people can also have the same birthday, or there can be two such pairs. Two birthday coinciding, two more birthdays coinciding, or three more birthdays. So many different events will come. All this is okay with me. I am telling at least two people will have the same birthday. That is difficult to compute. Instead, if I find no batch and then take the inverse, they will include all of them. So this is what happens, which means that even if there are 23 people in a house, the probability that they will, at least two of them will have the same birthday, there is a 50% chance that they will have this. This is not an intuitive one or a common sense way of looking at it. So this is that probability will come. Okay. You tell me when I have to.
Oh, okay. Thank you. 48.
I mean, go for some more.
48.
Okay, good. See, quick one more problem. See, you will know that. See, for example, someone we have a just a dot like that. Someone has to go and a dot like this one, and then where it falls, you are going to look. It is equally likely to fall in any one of them. Okay, and then if there is a particular circle in which if it falls, then you win, and so on. So this is of radius 10, and this is of radius 5. And what is the probability that we will win? Okay. So one way of argument is you throw a dot, it can fall anywhere, not outside, it can fall anywhere. Okay. If the distance of that dot from the center, okay, is equally likely to be any value, this is one argument. So if it is, if it can lie between 0 to 10 with equal probabilities in that range, so if it is between 0 to 5, I will, so the probability is. That is the way of argument. But the actual way I have to do is, I am looking at this area. If it falls in this area, I win, otherwise I don't win. So here there are incountably infinite number of points are there. You cannot assign the probability of each point also, because particular point has 0 probability, but only an area has got some probability. So the area is the one we have to use. Those are called geometric properties. You know that it is pi into 5 squared divided by pi into 10 squared divided by 4. So it's all very easy to figure out. So this is how you have to do it. There is one more thing. Let us say you have got two friends. Someone can dump all these things. There are two friends A and B. Okay, they decide to meet. Okay, in a common place or a park also, between 4 to 5. They will come randomly to that place. They have some prior engagement, they will come randomly over. And then they are telling that what if you come and then I don't turn up, what will you do? So you wait maximum of 15 minutes. If I don't turn up, you can, both of them decide after. So, what do you want to know? What is the probability that they will really meet? Okay, if they have this ability. So what we will do, this is 4 p.m., this is 5. The arrival time of anyone is equally likely to be 4 to 5. They will not come before 4 or after 5. When they come, they will definitely be there for 15 minutes. Before that, the other person turns up, they will have a meeting, otherwise they will go. The same is true for the other one. Then, what is the probability they will meet? So this is for A, this is for B. Let's look at how it happens. So if B comes here exactly at 4, at what range of values A comes, they will meet 4 to 450. So this range is allowed. If B comes at 4, 1, okay, that which means that A can come from 15 minutes from this point 4, 1. It can go up to 460. So this is allowed. Even this is allowed because what happens? A can come even 1 minute prior also. This is also allowed. So similarly, if he comes at 2, up to 17 it is allowed, and previously also it is allowed. So it should be clear that among any point of A's this person's arrival, 15 minutes ahead and 15 minutes below it's allowed. So which means that the area that we are looking at is an area of this kind, and if the arrival, each one takes place within that one, they will meet. Otherwise, they will not meet. So this is the area of interspace. In all these things, to compute the probability, we find the area of the region of interest divided by the total area. So that is easy to calculate here. This is 1 4, this is 3 4. This is also this is 1 4, this is 3 4. These two triangles are of same size. So the area of this one is 1 by 2 into 3 by 4 into 3 by 4. This is 1 4, this 3 4, this 1 4, this 3 4. This one, there are two such triangles into 2. So this is the region outside. So that is equal to 9 by 16. So probability of meeting is equal to 1 minus 9 by 16. Which is 7 by 16. Okay, fine. So we will stop.